Okay, so welcome to our lecture on physics and modeling of microelectronic devices. And in this lecture today, we are going to have a fundamental idea. Like, we are not going into the mathematical details of whatever I'm going to learn and whatever we are going to learn here in this part. However, this basic understanding will help you to answer several of the conceptual questions you might encounter in your interviews. Okay, so let's begin. So before we go into this, like we had already begun this in our previous lecture on the fundamental forces where we dealt with the gravitational force. Now let us understand. Let us imagine if you were looking through the eyes of an ant. Okay, think as if you are essentially. I mean, if you are an ant. Uh, which is essentially walking on a tub, okay, on a, let us say, on a vessel. Then if you notice, the ant, for that ant, the world of the ant is essentially, so what I'm, let me just give you some funny illustrations here. Here is a tumbler and here is an ant. Okay, now what will happen is, for this ant, the way it looks at the universe is essentially confined within this tumbler. Now let us, within this bowl, let us say some food is here and the ant is here. Okay. So now let us assume that you are essentially carrying this uh, with the hand. You can essentially carry this entire tumbler wherever you want. Let us say I was in Calcutta, now I'm in Hyderabad. Suppose this ant was inside my baggage. Then what will the ant do? It will be carried in the flight and it will essentially reach Hyderabad. Now notice the ant will be completely, how should I put it? Uh, I mean, it will have absolutely no idea that it has come from one part of India to another, isn't it? Think about it. Similarly, let us talk about the perspective of the coronavirus. Okay, so what does the coronavirus do? Let us say two persons are speaking with each other. One of them is having the coronavirus, COVID. The other one is not. Both of them are unaware of the situation, let us say. What will happen? The COVID will think that it is simply going from one person to another. Now, incidentally, the new person, let us say there is a person A, this is person B. B is affected with COVID positive. So basically, the coronavirus goes from B to A. Now, this A is an American, B is an Indian, let us say. This A essentially moves all the way, flies back to the US. Okay. And this A essentially meets another person C, where it transmits to the next person. So if you notice from the perspective of the COVID virus, it simply goes to the next person. Okay, the person who is very close to you, like within 1 feet distance. Now the point is that the COVID doesn't understand it has flew from all the way from India to New York, let us say, isn't it? So the point which I'm trying to make is that then later on in the newspapers it will come out that okay, the COVID has spread from India to the US. No, no, no. COVID has spread from the next person only. Okay. So the person A is called the vector, the person which is carrying it. Similarly, if you notice, if you remember in your school days, you must have learned malaria. Okay, the protozoan of the malaria disease, it is always being carried by the mosquito, but the mosquito is not affected by malaria. Okay, the mosquito is simply a vector, which is just like, let us say, a delivery person. Okay. So the point which I want to make in this silly comparison is that the way you look at the world is always limited by your senses. Okay. So the way we perceive the world is always limited by our senses. Meaning that for us, for every human being, the reality is essentially defined by our senses. Okay. So for example, if you are looking at any solid object, okay, you will say that okay, this wall is a solid thing in front of me. Okay. Now, an electron will say, he will simply joke at you. What, man? You are saying the wall is solid? I have got enormous amount of empty space inside that solid mortar where I can move. You will say that, okay, the metal is a solid. The electron will say, is really? I can find all empty space inside that metal lattice. Then again, if they, and you will think that, okay, electron is a solid. Is it so? Then we will go to the realm of 10 power minus 15 meters, that is femtometer order. Then the quarks will say electrons, really, electron is also empty space only. Understood the point which I'm trying to make? So essentially, whatever is solid, whatever is liquid, whatever is gaseous in our eyes, okay, is basically, we say that blood is liquid. Really, you look inside a microscope, you will find so many solid particles flowing inside the blood, isn't it? So if you look at water, it's a liquid because you are looking at it. So from the reality perspective, the reality what we look around us is defined by our senses. Please understand this very very crucial concept. Okay, so that means आपके लिए जो सत्य है, जो नेचुरल है, वो सिर्फ आपके परसेप्शन के ऊपर निर्भर है. Whatever you can perceive, whatever you can perceive through your five senses, that's it. Okay, whatever you can see, feel, touch, smell. So only those five senses will define the reality for you, for us. Okay, so that is what, for example, you might be thinking, how can COVID enter us? We are all solid particles. Is it really so? Remember, COVID virus is a virus. Its size is much lower than micrometer. So it can essentially penetrate even inside your living cell. A cell is in the order of micrometers. Okay. And a virus is even smaller than that. Virus is nothing more than a protein molecule. All right. So for a virus, even a human cell is like a lot of space, a huge space. In your IC fabrication, in IC fab, Parikshit sir will definitely teach you something about the class of the clean room. Have you learned that in your classes?
Yes,
Yes.
yes.
Yes,
Yes.
sir.
Excellent. So if you notice about the definition of the class, you will be defining the number of particles which is larger than 1 micrometer and so on, so on and so forth, right? So why about that? Like 1 micrometer is like not the reality for you. You can't even perceive it. But when you are dealing with a nanometer scale device, for that 1 nanometer is 1,000 times larger in dimension. So even a 1 micrometer, one dust particle of 1 micrometer is like thousands of devices on it. Thousands of devices on that dust particle itself. Forget about the IC. Is that part clear? So the reality is defined by your observation or the observer. So now let's begin with this over here. So when you are talking about the gravitational force, what is the range of observation you are dealing with? Light years. So essentially meaning that light years, but why am I telling you light years? Technically speaking, the largest distance which human beings can actually observe through Hubble Space Telescope is essentially in the light years uh, order. Okay. Now the point is, so I mean, we do not know specifically whether it is infinity or not. Somebody might say, okay, gravitational force is valid all around the universe, so it is stretching from minus infinity to plus infinity. Well, the thing is, we do not know. Okay, because we have been only able to, we means human beings have been able to fathom or measure up to light years. So that's why I have written specifically light years order. Okay, so this is the field or range. Now, the interesting thing about the electromagnetic force, and as we go along here, what happens is the range or the field of these forces are essentially much, much lower. So electromagnetic forces will essentially predominate in the order of micrometers and lower. Okay, so now you can realize that we human beings, what is the order we belong, like what is the reality for us? We belong not in light years or in micrometers. We are somewhere here where our order is in the, our dimension is in the order of 1 meter. So suppose somebody is between 5 feet to 6 feet tall, they will essentially be within the order of 1 meter. Okay. So if we are in this range, okay, we will never be able to observe any of this electromagnetic force, weak, or all this quantum theory will not be valid for us. So all these three forces which we have written over here, electromagnetic force, weak nuclear force, and strong nuclear force, these are all explained through the quantum theory. So this is one of the answers which you must give to your interviewer if they ask, like, we human beings, why don't we encounter quantum mechanics in our daily life? The answer is very simple. What will you say? You will say that the forces or the fields in the quantum theory, they deal with fields or the ranges which are prevalent in the ranges less than micrometer order. Whereas we human beings perceive the world through our senses, which are accustomed to seeing, looking at things in the order of meters or centimeters at the most. As a consequence of that, we never encounter quantum theory, quantum mechanics in our daily life. Is that part clear? Okay, excellent. So now we come to the electromagnetic force. Then if you go to the nanometers, so even much smaller than that. So what is the order of the electromagnetic force? This is a solid state material. Okay, so electronic devices and all that, they will essentially fall under this domain. So this course particularly is in the physics and modeling of microelectronic devices. Microelectronic devices fall in this category, micrometer. Okay, so if I taught you something around something in the lines of nano, like physics and modeling of nanoelectronic devices, nanoelectronic devices will fall in this category as well. Okay, and that is the consequence. As a consequence of that, in nanoscale electronic devices, we often encounter quantum mechanical theories. For instance, tunneling is there. So in my research group, we are working on something called tunnel field effect transistors, tunnel devices, and all that. So they are all falling in the domain of this. So for example, the devices which we make will be 45 nanometers and lower. Okay, so in these kind of orders, for example, in current day technology, we are dealing with 7 nanometer technology node. Okay, so in this nanometer scale, we will be encountering quantum mechanical phenomenon like tunneling and many other aspects. I do not want to kind of discuss this right now. So we will encounter many of the tunneling effects. Okay, when we are dealing with this order, 10 power minus 9 meters or nanometers. Okay, so please remember at the very onset itself that modern technology belongs in this domain. All right. However, this course is limited only to these devices, micro scale devices. Okay. Now, 10 power minus 9 meters. So what is the order which you can think about? This order is in not exactly in the domain of atomic structure, because atomic structures will be essentially angstrom unit, that is 0.1 nanometers order. Okay, so if we think about like 8 or 10 atoms arranged uh, in a single layer, then you will essentially encounter this kind of a dimension. Okay, now we come to the strong nuclear force. The strong nuclear force has the field or the range in 10 power minus 15 meters. So this order is in the atomic nucleus. Okay, atomic nucleus falls in this um, in this kind of range. Fine. So now we essentially come into the understanding with respect to the strength of the forces. Now, if you notice that there are, as I told you earlier, half integral spins are for half integral spin elementary particles are valid for matter. For the forces, you will always have what? You will always have integral spins, 0, 1, 2. Okay. So now if you notice that these are forces, so we will only have 0, 1, 2 over here. Okay. So for the gravitational force, it turns out, I'm not going into elementary particles here. So if the range is very high, the mass of the particles are essentially very, very low. It's inversely proportional. So as a consequence, gravitational force, its range, if you notice, extends through light years. So these are practically massless particles. So if these are massless particles, I mean, these kind of elementary particles are called gravitons. Okay. So if these are massless particles, so as a consequence, they will have the weakest strength. Okay. Now, till date, like scientists have not yet been able to find out anti-graviton or a repulsive gravitational force. And because of this always attractive property of the gravitons, what happens is larger the mass, the gravitons forces, the gravitational forces simply add up because they are always attractive. As a consequence, larger the mass, larger will be the gravitational attraction. Okay. On the contrary, all the other forces which we see over here under the quantum theory, we have been able to find out that they always have a repulsive part as well. So that means if you have two electrons, they will repel. Whereas if you have an electron and a nucleus, positively charged nucleus, they will attract. And this is the reason why you will always attain an equilibrium inside the solid state. How does it happen? Let us say you have already read this in your high school. So here is an electron, atomic nucleus, and here is an electron. Okay. Now, if these atoms, I mean, I will come to the solid state part later. If these atoms are very far off, okay, then what are the various forces which will be acting? One will be repulsion, electron-electron repulsion. This is force number one. Correct? Then, now force number two will be nuclear-nuclear repulsion. Correct? And finally, what are the attractions? This electron nucleus attraction, electron nucleus attraction, and similarly here you will have this electron, this nucleus attraction, and this electron and this nucleus attraction. Okay, so now you are essentially able to find that there are 1, 2, 3, 4 blue color attractions between positive and negative charges, and 1, 2 nuclear-nuclear repulsion and electron-electron repulsion. So all these attraction and repulsion will cancel each other out at equilibrium, giving you an optimal distance between the two nucleus. Okay, it turns out that this distance is essentially the reason why you get covalent bonds. Well, this is the reason why you will get the lattice constant inside the solid state material. We will look into this from the perspective of energies. So that will be much more solid understanding. Right now, this is just a subjective understanding. Like why solid state even exists is because of this. So we should thank God there is both attractive and repulsive forces in nature in the quantum world. As that is the reason why these both attractive and repulsive forces will always give you an equilibrium state. Okay, everybody. So this is the reason why solid state even exists. There is an equilibrium distance between the atoms inside a molecule, inside a solid state crystal lattice. All right. We will look into this in much details later. So both attractive and repulsive, they will cancel each other exactly at the equilibrium position. Okay, very good. Now, what is even more interesting is this fact. Like the electromagnetic force is 10 to the power of 42 times larger than gravity. Okay, so it means that the atoms and the electrons which are in the solid state, they are essentially held together by this electromagnetic force. Cool. Now, suddenly, if you come up with something by which you can simply cut away all this these bonds by some means, what will happen? These bonds are essentially these ionic attractions, repulsions, and charge sharing, whatever. These interatomic phenomena, the electromagnetic forces which are inside the lattice, they are essentially 10 power 42 times larger than the gravity. But somehow, if you can cut this connection, what will happen? Then gravity will play its role. You understand, no? So, I mean, the only reason why the atoms do not fall off from their lattice structure is because they are held together by the electromagnetic forces, because they are much, much larger. So essentially, if you have, this brings us to the earlier question, like if the only reason why solid state matter exists is because that there is always an equilibrium distance between the atoms, which are held together by the weak nuclear force, strong nuclear force, and electromagnetic force. These are all defined with quantum theory. ठीक है ना? Unfortunately, or if somehow you can break these forces, what will happen? Then gravity will take its will do its duty. Okay. The only reason why the ceiling above your head doesn't fall off because quantum theory is keeping it together. So small earthquake, what happens? If somehow this bond is broken, then gravity will take care of the two tons. Okay, very nice. So please remember this order. This is 10 power 42 times that of gravity, which is huge, isn't it? All right, now we go to the weak nuclear force. This is again an atomic phenomenon, which primarily leads to radioactivity. This is what gives you, let us say, X-rays, gamma radiation, alpha rays, and all that. So notice that this is happening at the order of nanometers. Now again, attractive repulsive, the theory was essentially developed by Abdus Salam. I do not know if you have heard this name. Abdus Salam is probably the most famous Pakistani scientist of ever. Okay, although he worked, I think, in Cambridge, but anyway, so he was responsible for the theory behind it, Victor bosons. I think he won the Nobel Prize for this. And I'm not going into the gravitational force. You have already learned it in your high school. Electromagnetic force, you will learn it way much more details than in this course in your electromagnetics. Probably you had a physics course also, right? So you must have studied the Maxwell's equations. All right. Now we will come to the strong nuclear force. Even more important than the weak nuclear force is something which is even crucial. Inside the atom, all of you might be knowing that if there are n number of electrons here, so let us say 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons are there. I mean, I'm not bothered about which orbital and all that. 1s2, 2s2, you can think about it. Just assume that we are having 8 electrons in the orbitals, okay? So it is supposed to have an equal number of protons inside the nucleus. We all know that. So I will do is I'll just draw the plus charges here. 1, 2, 3, 4, 5, 6, 7, 8. All right. Now my question is, we have told you that nuclear repulsion happens. Then these are all protons, my dear. And that too, they are all in the order of 10 power minus 15 meters. Nucleus is that, this is the size of the atomic nucleus, okay? This is the order of the size of atomic nucleus. So if this is the order of atomic nucleus, so how come all the protons, which are all positive charges, how can they stay together in this particular small region of space? They should also get Coulomb repulsion should happen, right? You are compressing all the protons together. Let us say you take the case of any element. Can anybody answer this question?
And also there are some neutrons inside the nucleus.
But the neutrons, they are essentially like neutral. So let us not bother about it. Can anybody explain how come all the protons are essentially staying together, even though all of them are positively charged? They should also get like repelled, isn't it? What is stopping them from repelling?
So because a strong nuclear force acts in that range.
Yes. So now the strong nuclear force, it turns out this particle is called the gluon. Okay, this elementary particle gluon, what it does is it essentially converts the protons into neutrons and vice versa. Somebody said neutrons, right? So these protons are going to simply transfer, it's like protons will come into neutrons plus G minus, as the case may be. Okay, so these gluons are essentially the factor which essentially keeps the protons together. Now, the reason why this gluon will act only at 10 power minus 15 is that the gluons are the most massive of all the elementary particles which you see. And as a consequence of that, what happens is, since the gluons are the most massive ones, remember, gravitational force, the gravitons are massless. As a consequence, they will extend to light years. Gluons, on the other hand, they are the most massive of all the elementary particles. As a consequence, what will happen? Their range is only between intranuclear protons. Okay, they will exert its field only within the atomic nucleus. And now this is the strongest one. I do not have the data about how large it is. I do not know much about that. I'm not an elementary particle physicist. So this gluons, they will be so strong. For example, if you notice, it is 10 power 42. This may be even 10 power 42. This may be even 10 power 42. So what happens is this new strong nuclear force due to gluons will be much, much stronger than the electromagnetic force. So as a consequence, even though the protons will be repelling each other because of this repelling electromagnetic force, Coulomb forces, the nuclear force will still keep it together. It's the same way as, even though the ceiling is like several tons, it doesn't fall off because electromagnetic force, being much stronger than gravitation, it is going to keep it together. Okay, so whenever you look at any solid state matter, the atoms exist. Like whenever we are speaking about this particular strong nuclear force kind of things, we have to remember that we are speaking in terms of the atoms, the stability of the atoms. Okay, so the atoms are stable thanks to the nuclear forces. The solid state is stable because of the electromagnetic forces. Okay, and the earth and the solar system is stable thanks to the gravitational forces. Okay, I think that's all. If you are interested, we can take it up some other time. So the whole point of this discussion for the last half an hour is that every force has their own field or ranges defined by its own property. It turns out that we are somewhere here between micrometer and light years. So for us, the reality is that we are all governed by gravitational force. So if we have a ball in our hand, a deuce ball or a tennis ball, and we throw that ball on the wall, we do not expect the ball to go straight through inside the wall because we are all in the domain of classical physics. Now, if we somehow reduce ourselves to the size of an electron and throw a ball, we will find that the wall is hardly an obstacle. The wall is full of empty space. The ball will straight away go through the wall. The ball, the tennis ball, which we throw, it will go straight inside the wall. And that phenomenon is called tunneling. We will look into tunneling later on at a later stage. Okay, so it means that whenever you are shooting bullets, for instance, even the bullet happens to be in the classical domain. But if you are shooting a bullet of electrons, that is quite possible in today's technology, then essentially it will be a scanning tunneling microscope, STM. Okay. Anybody has any question, you can ask, and then we'll.
So, you said that forces are because of integral spins.
Yes.
Here are integral spins, but why every force has a particle and elementary particle? Again, in gravitational force, under gravitational force, there are matter particles of spin half.
Yes, yes, yes.
So
I'll tell
basically,
you about.
yes, sir.
Yeah.
Yes, sir. That's all.
Okay. So the question I want, like this question is very interesting. So there are two kinds of things over here. Notice. Let me explain it in this way. One is, let us say, how do you define color? Anyone? For example, when we say that the plant or the leaf is green in color. So what does it essentially mean? Is it the green light which is reaching your eyes, or it is the leaf itself is green color or something?
It is
Green
the
light, sir.
wavelength that is reaching out.
Yes.
It's
Now,
reflecting blue.
basically what it means is whenever we are essentially speaking about any color, we are essentially, the physics is behind the pigment which is producing that color. Sir, why knowing the spin of particle? Yeah, I'll come to that. So that is essentially coming to statistical mechanics. I'll come to that. So here it is mainly about quantum mechanics. Statistical mechanics is something which we will deal later. So now, as far as this understanding for the color is concerned, let us get back to that. For example, what is the green pigment, the chlorophyll inside, chlorophyll on the leaf does? Whenever white light falls, it will absorb all the frequencies, all the wavelengths of light except the green. As a consequence, the green color or the green light, green radiation is scattered. And that green colored scattered light, scattered radiation essentially reaches our eyes. So if we talk about, there are two things involved over here. One is the photons which are reaching our eyes, which have the wavelength of green color. Okay. And the other aspect is the pigment chlorophyll, which is there on the leaf, which will absorb all the frequencies of white light except the green. Understood, everybody? Huh? So that means the light which is falling on the green leaf, if it is white color, say sunlight, then there are two aspects which essentially leads to the green color sensation which we are having in our eyes. One is the pigment chlorophyll, which will absorb all the light frequencies except green. That is the first thing. And second thing is that our eyes are sensitive to that green radiation, scattered one by the leaf. Okay. Now the green radiation which is reaching us, that is basically the photon. Here. Okay. Now the chlorophyll is essentially taking the case of these particles. So chlorophyll is what? If you go into the chemical structure of chlorophyll, it will be a molecule, correct? It will be a very complex molecule. Now, what happens is whenever white light falls on the chlorophyll, there will be some radiations. These are? There will be some energy states. The electrons will simply jump from higher energy to the lower energy states. And this energy difference is essentially given out as the green color. Okay, it's basically scattered radiation. We will understand about the scattering and spontaneous emission and all that later when we do optoelectronic devices. So now let us understand that this scattered radiation is what we observe. However, notice that this is basically the H nu of the green color, which you can see in your eyes. Okay, this is so basically the medium of the force, electromagnetic force is the photon. However, this is being released thanks to the electrons, which are essentially jumping in the chlorophyll molecule. Okay, so the reason why this electromagnetic forces are generated are because of these electrons, protons, quarks, or the charged particles in general. Okay, so that means when we have two charged particles, let's not bother about such complicated things. Take the simple case of the very old, like school level example, like you have a rubber comb and some small pieces of paper. Okay, let's draw that. You have a rubber comb and small pieces of paper will stick with the rubber comb when it is charged, isn't it? So what happens? There will be electrons which are essentially getting attracted between the positive and negative charge of the paper and the rubber comb. Okay, now these electrons are essentially causing the generation of this photons, or all these electromagnetic forces. However, you can understand that even then you can ask, sir, if there is photon over here, why don't we see it? That is because the frequency of that photon it does not belong to your visible spectrum. Okay, So that is the whole point. Similarly, you will be having the matter particles. So the matter particles will essentially give you the gravitons. Gravitons are the particles for the forces, for the transmission of the forces, just like photons. However, the matter particles or the mass particles, they are the reason why the gravitons originate. Sir, where can we find graviton? These are gravitons are essentially generated by all mass particles, as I said. Okay. Similarly, all charged particles will essentially give the photons and phonons. Okay. Weak nuclear forces are essentially generated by the radioactive properties. Then the strong nuclear forces are generated by the protons. As I told you, protons will essentially uh, transfer into neutrons, and neutrons will again transfer into protons, either giving or taking up the gluons. Okay, so essentially meaning that we often talk in terms of, for example, when we say that we drop something in our hand, it will essentially fall down on the ground, correct? So essentially, the other way, the physical way of understanding this phenomenon is that the moment we drop something, Earth is essentially pulling that matter towards itself, isn't it? Towards the ground. That's why things fall. Now, when the Earth is pulling it towards itself, what is the force that essentially pulls it? We will say it is gravitation. Okay, like elementary particle physicists will essentially think in terms of elementary particles, and they will explain the gravitational force in terms of the exchange of gravitons. So now you will ask, where can we find the graviton, like somebody asked right now? We will find the gravitons between any mass particles. So if it is a ball, you drop it, it will bounce back. If it is a glass material, you drop it, it will not bounce back, it will break. But that is a property of the solid state material over there. That is defined by quantum mechanics. That's material properties. Okay. Where, whether the coefficient of restitution is so high that it is essentially going to bounce back like a tennis ball, or else it will essentially break, is a material property defined by the solid state, electromagnetic force, and all this. Okay. But it will inherently be attracted by the earth, and essentially it will fall on the ground, is defined by gravitational force. As simple as that. Okay. Now this force transmission happens through graviton. Similarly, the light which you see right now, which is reaching your eyes, they are all by photons. Okay. Now, why is the reason for that? What is the origin of the photons? Are the electrons or the charged particles? I should not say electrons. Any kind of charged particles will essentially generate these electromagnetic forces. Okay, is that fine? Excellent. Sir, does elementary
So
particles vary
particles
applicable only
are
to solid? No, no, no. Elementary particles are elementary particles, as I told. Like if it is a force will act even inside water. So I mean, it's always there. Okay, so forces, so definitely it will act everywhere. Even the half integral spin matter particles. Okay, that will depend on the state of that matter. Okay, some matters you will find that I mean, all the matters will essentially have some range of their interatomic distances, which will define whether it will be in solid state, it will achieve its equilibrium in the solid state, or it will achieve its equilibrium in the liquid state or in its gaseous state. We will look into that when we deal with solid state after finishing quantum mechanics. Okay, so these elementary particles will be independent of the state of the matter. Okay, it's always there. So as I told you, for us, for example, if you speak to a person in India, we will say, okay, water is liquid. Believe me, I was in Canada for a while, and I spent a lot of my time in Switzerland. Okay, in Switzerland, around 4 to 5 months, water will be in the ice state. Okay, we used to go skiing in the Lake Geneva. So the entire lake will be like a skiing rink. So it will be so flat because the entire water of the lake has solidified. Fine. So if you ask somebody from North Europe, say Sweden, Finland, and all that, then over there the people will essentially say water is ice. Okay, so it's basically, as I told you, please remember at the very beginning of the class, I told you, now the reality for a person is defined by his or her own perception. ठीक है ना? So, like, if you go to the North European countries, for them, winter is like hell. Okay, but in India, we all wait for winter to come. Okay, so it's like this. So for us, if you say winter is excellent, the best time of the year to travel, to go for tourism. In Europe, for them, they will say summer is the best time for them to. Like, in fact, there is a saying also: if winter is here, can spring be far away? Okay, so because for them, winter is very bad. So the reality of a person is defined by the way he or she perceives the world. Just like the ant, for the ant it doesn't matter. For example, you are in an elevator, let us say in a lift, okay, and there is a mosquito. Or even better, suppose you are driving in a car and that car is inside in that mosquito is inside the car. What will happen? You are driving all the way from Hyderabad to Delhi. Awesome. The mosquito doesn't even realize it is inside your car, coolly enjoying the drive with you. Okay, now, so for the mosquito, it doesn't even realize, it doesn't even perceive that it is also traveling. Okay, so the reality is always dependent on the observer and the observation, and that is why quantum mechanics is an enigma for us, because we are in this domain, which is under the domain of gravitational force, and that is the reason why the entire quantum theory is only 150 years old, and that is what defining the entire technology that we have today. All right. Okay, let's start with the other one. Otherwise, we will run short of this. We will at least finish off this particular topic. Okay, so I think the last couple of lectures was kind of fruitful in the sense that you have got a clear understanding of the way we look at the world around us. And the truth is not necessarily what we see. The truth is beyond our senses. For example, if you cannot see the air, it doesn't mean that the air doesn't exist. Okay, it is simply limited by our eyes. If we cannot hear anything beyond, let us say, 2 kilohertz, it doesn't mean that sound doesn't exist beyond 2 kilohertz. All right. So, in fact, that is the reason why we need technology to help us. Okay. If we cannot see beyond 2 kilometers, it doesn't mean that the world ends at 2 kilometers. Okay, that's why we need a telescope or Hubble Space Telescope. If we cannot see less than say 0.1 millimeters, it doesn't mean that the universe is the smallest entity in the universe is that. Okay, we have been able to explore till femtometers. Fine, let's get back to this part now. Previously, we have seen the formulation of the Schrodinger equation, okay, and thereafter the time-dependent form, and then we even understood why the time-dependent form is unnecessary for our device consideration, and we will essentially in relativistic quantum mechanics. By the way, let me just be like for the completion's sake. For relativistic quantum mechanics, okay, quantum gravity consideration, you need to bother about time-dependent Schrodinger equation. But as long as you are kind of limited by, I mean, as long as you are dealing only with VLSI devices and all that, solid state, you are only bothered. You need to get bothered only about the time-independent form, because the time-dependent form simply influences the phase, not the amplitude. Okay, we are only concerned about the amplitude because we need to bother about the number of free carriers inside the material. Okay, na? Awesome. Like in the next class, we will begin with applications of Schrodinger equation. Then we will only deal with, as you can see here, time-independent form of Schrodinger equation. All right, so this is kind of important, probability current density, because this essentially deals with the question like, okay, This time independent form of Schrodinger equation tells us the availability of free carriers inside the material. Okay. So if we understand with that, what we understand is suppose there are n number of electrons generated over here. Cool. But what is the probability that n electrons will essentially move to the other part of the material? Understood? So that is why we will say probability current density. So probability essentially is referring to the probability of availability of the free carriers. Okay, na? So once the free carriers are available, then we need to ensure that the free carriers are moving. Suppose the free carriers don't move. तब क्या करोगे? खाक करोगे क्या? आपका करंट ही नहीं आएगा. Do not forget your final goal. Your final goal is to develop a device which will essentially work as an active component of your circuit. You know? So active component matlab it should conduct currents and all that. ठीक है ना? Excellent. So our objective is to find that given that we have essentially found out through the solution of the Schrodinger equation the availability of free carriers, now we are telling that given that there are available free carriers, what is the probability that they will essentially move? They will essentially create one current. Okay. So now we will explain like the probability of existence of the particle in a volume A into dx. So यहाँ पर हमने क्या किया है? Suppose we have taken a block of material. It can be silicon, it can be metal, it can be anything. ठीक है? Now A is the cross-sectional area. All right. Of course, I'll give you one what should I say, disclaimer at the very beginning. Whatever proofs of Schrodinger equation and whatever proof of this probability current density we are doing, this is a very like the simplest possible way of explaining these things. We will deal with the most difficult derivations and all that when we deal with the real devices and circuits. Okay, now? Because we are all circuit engineers here, device engineers here. Okay, so as far as physics is concerned, I am going to give you the minimum necessary for your understanding. Okay, but please remember, if you can explain these things in your interview panel, your job is secure. So if there is an area A into dx is the differential length, then in this certain volume, what is the probability of existence of this? Remember psi star psi. Okay, now here is one aspect which I have to explain. Let us say you have got, oh sorry, excuse me, suppose you have got A plus IB. Okay, this is X. So the complex conjugate of X will be how much? Just the imaginary part will become minus. And so now instead of A, if I write cos theta plus I sin theta. Okay, then what is the X star? Cos theta minus I sin theta. I will just change the symbol in front of the I. Cool. Now this is nothing but e to the power of I theta. This is equal to e to the power of minus I theta. Okay, now. So similarly, if we have psi is equal to a e to the power of I, let us say theta. Okay, then psi star will be how much? A e to the power of minus I theta. Okay, now. It's just pure complex algebra, nothing else. Similarly, what is this psi star? Psi? The psi is what we have already seen here. Okay, this is what we have dealt with earlier. All we will do for the complex conjugate star man, we will just put one minus sign here, like this. Fine. So what we are trying to do is, so psi star psi क्यों कर रहे हैं? देखो, अगर हम psi star ये है ना, and if I multiply psi star a e to the power of minus I something, and psi is a e to the power of plus I something. This plus I and minus I will cancel and you will be getting only a square. That is the amplitude square. That's what I told you in the very first lecture. Okay. So that essentially defines the probability of finding that carrier. It can be electron or whatever between x plus dx within this particular volume. Okay, now. So now what we shall do is, this is the original Schrodinger equation. We have seen that. I will simply multiply both sides with psi star here, and the way we have obtained this Schrodinger equation, you can do it in your home. Okay, you can apply the same formulation for the Schrodinger equation. For example, you take the derivative with respect to x, take the derivative with respect to t, and then equate the energy Hamiltonian. Okay, you will essentially end up getting this relation. Okay, here with, if you notice, here is the minus I. Apart from that, the entire equation remains the same as the original Schrodinger equation here. So all we will do is we'll multiply psi on both sides of the equation. Here I'll multiply psi star on both sides of the equation. And then we will do some algebra. We will just add the left hand side. So it becomes psi star del psi del t, IH cross. There is one IH cross with a minus here. So if I'm subtracting this, what will happen? It will become plus psi del psi star del t. We are subtracting this. So minus H cross square twice n, and you will get this. Psi star Vx psi and psi Vx psi star, they will just cancel. Okay. Now, once we have this relation, then you can clearly understand that psi star del psi del t plus psi del psi star del t is nothing other than this particular product. Okay. Then IH cross, and here it is minus IH cross, minus H cross square. So essentially this is like IH cross whole square. So one of them will get cancelled and you will be left with this one. This will essentially lead to, if we make a, I mean, instead of this, I can del del x, I can take it outside. And this del x, I can take it as an integral on the left side. Okay, you can see this. If you find it slightly difficult right now, just go through it. This is just pure algebra. That's the reason why I wrote all the steps here for your understanding. Okay. Now, once you have reached over here, then notice the probability current density, which is usually denoted by S, is defined by minus. Why minus here? Can anybody tell? Okay, we don't have time now. So this minus is because this probability current density essentially refers to the number of carriers lost. I'm emphasizing this word lost inside the material. Okay. So let me just write it here so that, so number of carriers, free carriers, let us say. Free carriers, that's the reason why they're able to move in the first place. So free carriers lost, that's why it is minus. Okay. So free carriers lost, because देखो यहाँ पर क्या हो रहा है, यहाँ पर कुछ carriers आए थे. Now what we are trying to do is that if the carriers move from left to the right, then the number of carriers will be less over here and few carriers will be here, right? So the number of the rate of loss of the carriers is what is defined here by the probability current density. Okay. So that's why we have put a minus, and then so number of carriers lost with time, so del del t of the probability of finding that electron, that is what we have defined in here. So in fact, the rate of particles lost per unit area is defined by this. So I have just written that equation here. Now, from our algebra, we have already proven this. So this will be equal to this relation. Okay. Now, if you just put, okay, ether is like, it's nonsense. Okay. Anyway, I'll explain that in a minute. So once we have got this S, then what we shall do is, there is a minus I. Minus means basically -1. So you can basically convert this into plus and make it I square here to remove that minus sign. And you can cancel this one I with the I square. Okay. That's why you have got one I here, 2mi and H cross. And then all I did was, instead of del psi del x and del psi star del x, I have simply put the expressions for those relations which we obtained in the previous lecture. That's here. Okay, IP H cross, where is this? So I have just put it in here, and this I and all those cancel out, and finally you reach out this. So what is the point of all this exercise? आप सोच रहे होंगे सर हम ये algebra क्यों कर रहे हैं? Basically we want to get this relation here. Okay. Now if it is psi star psi, it is nothing other than you can simply replace this by, okay, the amplitude of the psi function uska square karke h cross k by m. Okay, this is one formula which you can keep in mind. How it has arrived is basically this derivation, small derivation. Okay, because whenever we are trying to deal with like tunneling phenomenon, okay, let us say even the barrier, in fact the applications, large rectangular potential step, and in fact in this week itself we will begin with our laboratory sessions, right? So in the lab assignments, you will have to develop the models for all this Schrodinger equation applications. Initially, I thought of giving you a lab exercise on like design a simulator which will solve the Schrodinger equation for certain cases, but I thought it will be too much at your stage. Like you don't need to bother about Schrodinger equation that much. If you had been, if I were teaching you physics, or if you were from physics background, I would have asked you to solve the Schrodinger equation itself. Okay, but that's not the point of this course. That will not be asked in your interviews also, so let's skip that. However, the application of Schrodinger equation, which is very crucial, so we will look into that in our laboratory sessions, okay, laboratory assignments. So this is the expression which we need to bother about. So that means if you want to find the probability that the carriers will actually move inside that, so what you have to keep in mind is that ये size square जो है ना, that is essentially the probability that the carriers are generated at a particular location in the material, multiplied by h cross k by m gives you the probability that these many particles will essentially move inside the material. Okay, that's all for today. I'll just go through the chat box if there's anything. Okay, Runa Dikshit had asked, I have asked because you have been mentioning only solids throughout the lecture. Yeah, okay. The reason why I'm specifically referring to solid, because the whole objective of solid state, whatever we are studying here, is to understand the fundamental physics, why materials exist. Solid state क्यों है? Solid state तो समझना है ना? क्यों समझना है? क्योंकि silicon solid state है. Believe me, if silicon was a liquid, I would have essentially spoken about liquid only. Okay. All right. Bhagyashree has asked in the previous study, ether. Okay, this ether, as I told you in the previous lecture itself, after Albert Einstein, ether is non-existent. And fire, when it comes to which levity or gravity, this levity concept is gone. The physics behind levity is something called, anybody in the class? Whenever we see something levitate, something going up, it's because of buoyancy. Okay, Archimedes principle. So the amount of air or water which your system is kind of displacing, the weight of that amount of air, if it is heavier than the amount of material which that balloon holds, the balloon will go up. So that means if you are having 1 liter of hydrogen balloon, that means it has displaced 1 liter of air. So 1 liter of air will be definitely much heavier than 1 liter of hydrogen. As a consequence, it will basically go up. Instead of that, suppose the same hydrogen balloon, instead of hydrogen, you simply blow the balloon with your mouth. The kids do it, right? You blow the balloon with your mouth. Now, if you notice that our breath is having more of carbon dioxide, it turns out that carbon dioxide specific gravity is heavier than air. As a consequence, what you will find? The balloons which you inflate using your mouth, they will always gravitate, not levitate. It will fall down on the air, on the ground. In fact, you will find that babies, kids, when we were small, we used to play with balloons, right? The balloons will go up and it will fall down. And again, we will start banging on that balloon just because it's like a ball. Why? Because you have inflated it with your mouth. Suppose you inflate it with helium or hydrogen or anything lighter than air. Forget about it. The moment you leave the string, it will go up in the air. That's so the levitation ka physics, proper physics is basically buoyancy. Okay, it has got nothing to do with levity and all that. Those are all wrong concepts of physics during the Greek time. Okay, Sri Kamal, sir, how can we break the bonds between electrons? Suppose in case of earthquake, you said it breaks. Yeah, of course. What happens is all these, okay, it's already 11 o'clock. Those of you who want to leave, you can go. Okay, so Sri Kamal, sir, in fission reaction, how is the nucleus getting split even if it is a, yeah. So if you notice the fission and the other atomic reaction, nuclear reaction is the fusion. Okay. So in fission and fusion, you are essentially breaking the bonds using high energy physics. Okay. You are essentially making it happen. For example, in electrons, it is quite possible to break the bonds. You simply dope the material, electrons will come out. I know. So it is possible, but that will require lot of amount of energy to be kind of inserted. Lot of technological breakthroughs have to be done. Okay, that's all for today. Thank you so much. I'll stop the
Sir,
recording.
one small doubt.
Yeah.
In the very first progressive wave equation, you have